start. Okay. All right. So yeah, as I said, our focus will be to look at the theorem by Mirkovich-Villanen called the Geometric Satake Correspondence, and to sort of make sense of it, motivate it, and then try to outline the proof as much as possible within the time we have. So I'll start with a statement, and then sort of we'll go from there. Don't worry if many of the terms are completely foreign to you. That's kind of the point of why many of us are here, I think. And so yeah, so we start with an algebraic group C over C, which we take to be reductive and connected. When I say reductive, you can just think about the fact that its associated category of representations is semi-simple, so that all of our representations completely split into irreducibles. And then we'll have an independent field, which we check as a coefficient fields for our fields and for our sheaves and representations. So denoted by K, we assume it's algebraically closed and of characteristic 0. So these conditions are quite restrictive. Mirkovich-Villanen do this in much more generality for sort of certain types of rings of an arbitrary characteristic, but for our purposes, we just sort of work with the special case. And so the statement now is that there exists an equivalence not only of categories, but also of tensor categories, where on the one hand, we're looking at perverse sheaves on an object called the affine Grassmannian associated to the group G, taking coefficients in K vector spaces, together with a monoidal structure given by a convolution product. So that's the geometric side of our equivalence, and the other side is given by representations of what's called the Langlands dual group of G that we take to be defined over K, together with tensor product of representations. So in a sense, this is kind of much of what geometric graph theory does. It takes a category of representations and tries to interpret it in a geometric setting. And so, yeah, we'll basically try to get as close to a proof of this as we can in 5 days. So I've just sort of written out what things are right here. I've said some of these things out loud. I should mention that our representations are assumed to be finite dimensional, and that there are two sort of two rings we'll be focusing on to define the affine Grassmannian. On the one hand, we have the ring of formal power series with C coefficients and its field of fractions, which we'll denote by uppercase K. And then the affine Grassmannian will be defined as the quotient of G with O points modulo G with K points, which can be actually obtained as a direct limit of schemes. So we call that an int scheme. So the discussion of what the affine Grassmannian is and how its geometry behaves will be sort of where Alberto picks up. As far as today's lecture and tomorrow's lectures are concerned, the focus will be on sort of background on Rep G and sort of the basic theory of perverse sheaves. Some notations that may be useful later on is we sometimes write Sat sub G for the category of the geometric category appearing in the correspondence, sort of as the Satake category. And whenever it comes up, we'll usually assume that our groups are just matrix groups, meaning that they have a closed embedding into some GLN. And we'll assume that that we've chosen a torus together with a splitting that identifies it with just the product of GM to some power. Yeah, so that's sort of the notation we'll be using. As to why one might care about this theorem, so one of the reasons is, as I said before, this is giving us a geometric interpretation of the category of representations of any reductive algebraic group. And this is actually like stronger than that. The tensor product also gets a geometric interpretation, and that's actually the main input that Mirkovich-Villanen bring. The categorical level equivalence was already established by Ginsburg about 10 years earlier. And hopefully the categorical equivalence will be something that one can sort of intuitively conjecture once we're through the background of the first 2 days. The second motivation is it gives us a sort of canonical construction of the Langlands dual without sort of going into the combinatorial woods. We just sort of the equivalence just fleshes out the G dual once we start with G. And the last part is one which I'm not familiar with, but some people might be, is that this theorem is actually a form of the unramified local geometric Langlands correspondence. So it's kind of a starting point for going further into that direction. And yeah, so I guess I'll give a brief summary of a little bit, in a little bit more detail of what will be going on, at least for the next couple days. The first thing we'll do is we'll talk about the just overall proof strategy. And so the idea here is that really we're following kind of a general pattern that's called Tanyakian formalism. And that's kind of just a general way of identifying certain tensor categories with one another. And then from there, we'll go and actually build some prerequisites. First, on the representation theory side of things. So we'll talk about the classification of semi-simple algebras and the representations. We'll move to the algebraic group settings, talk about root datums and define G-dual, and then we'll introduce the while group and the Bruhat decomposition of the flag variety. So that's sort of what I'll aim to do today. If we can't quite wrap up, we'll just kind of go into tomorrow to finish that up, and then we'll move on to some background about the category of perverse sheaves. And here, to sort of focus on the categorical structure of perverse sheaves, we'll work with the slightly simpler geometric structure that is the flag variety associated to G rather than the affine Grassmannian, and we'll sort of describe the category of B equivariant perverse sheaves on that. And then Alberto will sort of be working with the affine Grassmannian analog. And so in particular, what we'll be doing is we'll start with sort of constructible sheaves and their derived category. We'll introduce the perverse G structure and define the category of perverse sheaves on B this way. And then we'll talk about the simple objects in that category, which are called IC sheaves, and give a definition of the convolution product that appears in the equivalence. So that would be the end of sort of my part of the talks, and then Alberto will pick up from there, and he will introduce the affine Grassmannian, talk about its geometry and the sort of Bruhat type decomposition it admits. And the last 2 days will be spent trying to actually prove the main theorem. So yeah, that's the idea. And I guess now we can get started. So the first thing I want to talk about is this notion of Tanyakian reconstruction that basically asks that if I have a category C that is symmetric monoidal, the question is, can I find sufficient conditions on C so that I am guaranteed the existence of a tensor equivalence between C and the category of representations of some algebraic group H with its tensor product. And Tanyakian formalism sort of answers this question in the positive. So I guess we'll start with the right-hand side, and we'll say, like, what are some of the visible properties of this category? So if you just
what is H here, Saad?
Oh, H is some algebraic group.
Thanks.
And K is the field we fixed at the beginning. Yeah. So if we look at the category of representations on some algebraic group H, so they're just vector spaces enriched with an action of H. We can see that it's K-linear, abelian, and that it comes with a forgetful functor down to vector spaces. finite dimensional vector spaces, which if you look at it, you can realize is exact. So it preserves short exact sequences. It's faithful, injective on Hom sets. Is that how? Yeah. And symmetric monoidal. It agrees with the tensor structure on either side. And once we've extracted sort of these conditions, work by Deligny, Milne, and let's see, Rivano tells us that actually, if I have an abstract symmetric monoidal category with these properties, so we call this sort of a Tanakian category. So we call sort of categories with this structure symmetric monoidal. We call this a Tanakian category. And a functor of this form is called a fiber functor. So it says if I have this data on an abstract category C with a fiber functor, then I'm guaranteed. So, okay, my bad. I forgot one last condition in terms of invertibility of objects in C. So the last thing we ask is that whenever I have an object X in C whose sort of underlying vector space is one-dimensional, I kind of flipped it. So whenever the dimension of the underlying vector space of X is one-dimensional, I'm guaranteed that X is invertible in C. So that's kind of what happens with one-dimensional representations over H. Then whenever I have this, I'm guaranteed that there exists an equivalence of tensor categories compatible with fiber functors between C with its monoidal structure and the category of representations over some affine group scheme H in such a way that the projections down to the fiber functors commute with this equivalence. Where here, where H is some affine group scheme. Defined over K. So that's sort of the theorem that gives us a roadmap. I have an abstract category, maybe of a geometric nature. I want it to be the category of representations of some over some algebraic group. The method is sort of check all of these adjectives and display a valid fiber functor. And then sort of Tanakian reconstruction tells you, okay, here's your category of representations. Now the group H that you get is still sort of abstractly defined in this context. And the idea is once you have this equivalence, you can then transfer information back and forth between the left-hand side and the right-hand side to learn more things about H. So for instance, you may have noticed that we haven't used semi-simplicity yet. That comes from the fact that G is reductive. So we haven't used the reductive hypothesis on G. Which is equivalent to rep G being semi-simple. So this is one of the ways in which, this is one place where we first prove that sort of the category C of perverse sheaf. So the Satake category is semi-simple and deduce under the Tanakian equivalence, let's say, that the group H that we're given is reductive. So that's one sort of first step towards identifying H, is it must be reductive because perverse sheaves on the affine Grassmannian will turn out to form a semi-simple category. And the second sort of information flow we'll exploit is we'll be able to identify the simple objects of the Satake category with those of rep H, and from there deduce that H is actually the Langevin dual of G under sort of general considerations of classifying reductive algebraic groups by their root data. So via the root datum classification. Of reductive groups. So that's sort of a first high-level sketch of how the proof goes. We have this abstract geometric category. We study its properties to get this equivalence, and then we flow information back and forth to actually get G dual on the right. So that's pretty much all that I'll be saying about the actual geometric Satake correspondence, and Alberto will continue on day 3. But for now, I'll be moving back to sort of like more elementary grounds and just giving some background on the rep theory and perverse sheaves prerequisites that are involved.
Hey, Saad, I have a question.
Yeah, go ahead.
So do we? Okay, so from this Knockian reconstruction theorem by Deligne, whatever, does that give us some information about the root datum of H, whatever H is? Is that how we get this last step?
So the theorem itself doesn't. You need to study the simple objects of C and then use, I think, this compatibility with the fiber functor to learn about the simple objects of rep H. And then those are classified by dominant weights in general for an algebraic group. So you have this is where the root datum kind of comes in.
I see.
Yeah.
Okay, thanks.
Good, yeah. Any other questions?
Yeah, what happens if you take representations of a non-affine group scheme? Is that still Tanakian?
So the only version of this Tanakian reconstruction theorem that I'm aware of gives you an affine group scheme as the output. So I'm not quite sure whether there are variants.
Right.
Yeah.
So perhaps like you plug in a non-affine group scheme and then if it's Tanakian, then its representations are tensor equivalent to those of an affine group scheme. So
I
mean,
see.
maybe it's like it's affinization or something.
That's possible. Yeah. I'm not sure, but that sounds fair. Good.
Thanks.
Yeah. Okay. So we'll move on to sort of a more elementary treatment, and we'll just talk about the representation theory of the algebras and reductive groups. So let's start with sort of reminders on semi-simple Lie algebras. Okay. So this is something that we'll be coming back to when we move to the algebraic group case, is that if you just take the Zariski tangent space at the identity of an algebraic group and equip it with a Lie algebra structure, you can just pass to a reductive Lie algebra, which is essentially just a semi-simple Lie algebra plus an abelian one. And in particular, you can just study much of the representation theory of reductive groups by passing down to the associated Lie algebra. So we start here and we sort of remind ourselves of what we know in this case, and then sort of come back to it in the future. So if I start with a semi-simple Lie algebra G, the first thing I usually do is I say, well, it naturally acts on itself by the adjoint representation. And if I restrict that to a choice of Cartan, I get an induced action by an abelian subalgebra. So let's, I guess, remind ourselves first that we always fix a triple H contained in B contained in G, where H is a Cartan subalgebra, which you should just think of as sort of the Lie algebra associated to a choice of maximal torus in the associated algebraic group, and B a Borel subalgebra, which is maximal solvable.
Hey, Saad.
Yeah. Could you maybe up your microphone a bit? I'm not sure I can hear you.
Yes, can you hear me better now?
Yeah.
Can you give me an example of like a G that we could be working through and what H would be and stuff?
Oh, sure, for sure. Yeah. So throughout, maybe you can think about G to be SL3, and then B to be the sort of upper triangular matrices, and H to just be diagonal matrices. So yeah, you can feel free to keep that in mind. And as we go, I actually meant to sort of illustrate some of the ideas with that. Yeah. So the Cartan subalgebra is just a maximal. You can think of it as the Lie subalgebra associated to a choice of maximal torus in G. The Borel subalgebra in the same way. And so yeah, once we restrict our adjoint representation to H, the fact that H is abelian gives us a sort of a generalized eigenvalue decomposition that allows us to express G as a direct sum of H and some generalized eigenspaces, G sub alpha, where alpha takes values in the dual of H of the Cartan, and is given by the set of generalized eigenvectors under this section, meaning that these are all of the points X in G, such that for any element H in H, let's see, H acts on X by alpha of H. So by scalar multiplication. And some terminology that maybe most of you are familiar with, but it is good to just set down is we call the alphas in H star for which G alpha is non-zero, the roots of G, the set delta, which is all such alpha, together with H star is called the root system. Of G. And here we equip H star with an inner product, with a non-degenerate inner product given by the killing form of G. And so this is something we'll be using throughout. Is the main reason, in my opinion, we just work with semi-simple things is this is non-degenerate if and only if G is semi-simple. Okay, so these are the roots and the associated root system. One thing we can look at is we can just sort of look at the Z-span of the roots inside H star, and we call that the root lattice. Yeah, so that's sort of where we start. We have our Lie algebra G, we act by the Cartan, we get this decomposition. I guess if you want to keep a picture in mind, in the case of SL3, we'll end up with 3 elements in H star, which we can call, I guess, alpha, beta, and gamma. And those will be the roots. No, sorry, those will, yeah, sorry, I'm getting confused here. Yeah, Alberto, can you maybe like jump in? Is it alpha plus beta?
Yeah, it's those and their negatives.
Yeah, right.
And gamma, the way you've written it, gamma will be negative alpha plus beta.
Right. Okay.
But yeah, it's those 3 and their negatives.
Right. And these guys are going to be the roots, and they're going to generate a copy of z squared essentially inside of H star, and that's going to be our root lattice. And essentially what we've done here is we've taken a Lie algebra, and by defining the set of roots and giving H star an inner product structure, we've obtained a sort of combinatorial structure. So through this, we can define sort of a mapping from semi-simple Lie algebras over C into the collection of root systems with an appropriate notion of isomorphism.
So Saad, maybe in the SL3 case, we can just mention quickly what alpha and beta are. So SL3 Lie algebra is traceless 3x3 matrices. So you can just take H to be the diagonal elements. So if we just call them A, B, and C, then alpha is just A minus B, and beta is just B minus C. And then, alpha plus beta is A minus C. So you get sort of all combinations of A, B, and C, where one of them is positive and one of them is negative, like B minus A, C minus B, then A minus C, and C minus A. So they're not too crazy.
Yeah. Yeah. Yeah, again, like the torus, yeah, is just a bunch of copies of C star in our case, and most of the sort of treatment we'll be doing is manipulating those entries. Yeah. And so, yeah, this allows us to map from semi-simple Lie algebras to combinatorial structures by sending a pair G, H to its associated root system, so delta, H star. And it's a theorem of Chevalier that the root system of G is independent of the choice of H. So this is actually a well-defined mapping. It doesn't matter which H I've chosen, which Borel I've chosen. And we have more structure. So I guess you can just look at the reference. Sarah wrote a book on the representation theory of complex semi-simple Lie algebras. That says that, well, we have an injectivity result that says that if G and G prime have isomorphic root systems, then the actual Lie algebras get an induced isomorphism. And then we have an essential surjectivity result that says every root system can be obtained, comes from some semi-simple Lie algebra. So we've moved the classification problem from the realm of semi-simple Lie algebras to the realm of root systems. And that's actually good news, because now root systems have a straightforward axiomatization. and they can actually be classified in the sense that simple, so irreducible root systems meaning that there does not exist a decomposition into two disjoint pieces such that the inner product vanishes for any pair of elements in the two root system, the two sort of components. So these are classified by Dynkin diagrams. And they correspond under the Lie algebra root system correspondence to simple Lie algebras. So these are what corresponds to simple Lie algebras. And then the decomposition of a given G into simples is unique. So with sort of all of these facts put together, we get a classification of semi-simple Lie algebras. So with rather minimal combinatorics data coming from just a single representation of G that just isn't like just comes for free, we can obtain a classification of semi-simple Lie algebras. And later we'll sort of develop the analog for algebraic groups. But before we do that, I'd like to say a few more things about sort of the root theory in this setting that will be useful moving forward. So the first thing I want to mention is the killing form canonically identifies this cartan with its dual by just sending an element through the functionally defined. And using this, we can associate to every root a so-called co-root. Which we denote by alpha dual. So that would be an element of H. And the way we define it is we define it to be the element of H corresponding under this equivalence here to the element 2 times alpha divided by the killing form applied to alpha n itself as an element of H star. So this might seem kind of strange at first. One of the motivations here is by construction, this element satisfies that the pairing with alpha equals 2. And we also have that for any two roots, alpha and beta, we have the identity that if I take the killing form of alpha and beta, what I get is the same as evaluating alpha on beta dual. So it's kind of a way of reinterpreting beta as something to be evaluated on with respect to the killing form. So this is kind of, we get a combinatorial structure that's attached to the root system. So we get a set of co-roots, delta dual under this association with the pair delta dual together with H, also getting the structure of a root system, which we sometimes call the dual root system. Yeah, so at least as far as Lie algebras are concerned, because the killing form just gives us alpha dual directly, we didn't need to account for any of this in the combinatorial structure. On the other hand, once we move to algebraic groups, these co-roots won't come for free essentially, and we'll need to account for them in developing an analog of this map from Lie algebras to combinatorics we defined earlier. And one last thing I want to talk about sort of in this section is the fact that is the classification of representations of a semi-simple Lie algebra using these notions of root systems. So the first thing to note is having chosen a Borel B, we get a decomposition of the set of roots into two parts, positive and negative roots, where delta plus consists of those roots appearing in the decomposition of B into root spaces. So that's G alpha. So once I've chosen B, I can look at it splitting into root spaces, and it just tells me here are some like special roots. And this decomposition is well behaved in that it's additively closed. And for any root alpha, exactly one of alpha, negative alpha, is in delta plus, where one of the axioms of a root system is that this is always in delta. It's a sort of closure under reflection across the hyperplane perpendicular to alpha with respect to the Killing form. One more sort of substructure here is we can in particular look at an additive basis which we'll denote by delta sub S of delta plus. So this is the smallest possible set which generates delta plus additively. And we call these the simple roots. Of G. And this is usually convenient because it just reduces the number of checks to make. If you have a check that's sort of linear, you just check on simple roots and you get the rest for free. So now, I guess there are two kinds. So now that we've sort of said everything there is to be said about the roots themselves, I should say that more general representations of G decompose. So let's call them V. So decompose with respect to the restricted action of H. In a similar way. So you can always write V as a direct sum of elements still in H star of generalized eigenspaces. So the V alphas are defined as before as sort of generalized eigenspaces with respect to a functional alpha. And so in all of these alphas appearing here with non-zero V alpha are called weights. Of V. And one of the features of the rep theory of Lie algebras is if you just study the weights of V, you can learn a lot about V. There are two particular classes of weights. That inform the rep theory of G in particular. So on the one hand, we have the integral weights. And these are sort of an extension of what you get by naively taking the Z span of the roots. So these will be denoted by gamma sub G, and they will contain the root lattice, which we defined earlier. And they're defined with respect to a pairing with simple roots. That says I will consider all of the possible weights which pair with each simple root to an integer. So that's the first desirable condition for a weight. And the second one is a so-called dominant weight. And these are defined as those weights which pair to every simple root to a non-negative value. Where, yeah, I guess that's as much as I have to say for now. Later on, we'll have a sort of more geometric understanding of those dominant weights and how they vary depending on which B we've chosen. But for now, you can think of them as having to do with the positivity in that they live in a cone that is cut out basically by the choice of B. If you think of it as with respect to these equations, it's sort of just cutting out different, with respect to different hyperplanes associated with those simple roots. And once we have this notation in place, we can state the classification theorem that says that if I have a semi-simple Lie algebra G, we have a one-to-one correspondence between finite dimensional, always, irreducible representations of G, and the collection of integral dominant weights. Of G, where if I check an irreducible representation V, I can split it into this generalized eigenspace decomposition, and I can locate a unique integral dominant weight lambda appearing in it and send it over here. And this is a bijection up to isomorphism on the left. So that's the first statement that kind of is relevant to the geometric Satake correspondence, at least in its algebraic group, as its algebraic group analog. It indicates to us sort of what sort of a basis for the simple objects of the category of representations on G. So that's as much time as we'll be spending just on the semi-simple Lie algebra settings. And now we'll try to move to algebraic groups and say how things generalize or correspond there.
Saad, just one short thing. I think this probably goes without saying, but just for clarity, you have to take lambda there to be like the maximal integral dominant weight. Like there might be many, but there's going to be one which is maximal there.
Yeah, that's a good point. Yeah, it should be the highest weight. Good. So now on to the algebraic group settings. So I guess we'll start with the root datum associated to an algebraic group. And the setup will be similar. We'll start with a connected reductive group G and a choice of Borel and maximal torus, which, if we pass to the Lie algebra side, gives us a triple as before. And again, you can think of SL3 here. This time, the torus will be elements with determinant 1. So we need the product of these three things to be 1. So that's the torus. And the Borel will still be upper triangular matrices. And now instead of the little add action, the natural action that comes for free now is G acts by big add on G. And restricting to the torus gives us, again, an action of an abelian subgroup on the Lie algebra G, my bad, onto G. And we get a root space decomposition, except this time we want the roots won't be functional on the Cartan Lie subalgebra, they will be functionals on G, also known as characters. So G splits as Cartan plus a decomposition with respect to what's called the character lattice of G, which will denote by X upper star G of G alpha, where now these X upper star G are the set of algebraic maps from the torus to GM, and G alpha is as before. So the set of elements such that G acts on X by alpha of Gx for all G. And so this, so far, very much the analog of the Lie algebra setting. We have, so you get roots delta with a root system where you can basically, if you have an algebraic map from the torus to GM, you can differentiate it and get a map from the Cartan to the ground field C. So you get a functional, so you can actually push the root system over to the Cartan subalgebra and then view it as a root system with respect to its surrounding H star. Now I have some doubt about whether we'll run into an issue with the fact that the killing form may not be non-degenerate. So maybe I shouldn't quite write the fact that this is a root system, but we certainly can view the set of roots as a subset of H star. And one thing we can start by observing is that these homomorphisms are actually quite rigid. The algebraicity condition tells us that this can be canonically identified with Z to the n if the torus splits as G to the M to the n, GM to the n. And the reason for that is that if you look at algebraic maps from GM to itself, this can be identified with Z under the identification that sends a map phi to that sends G to the n in the ring side to the integer n. So that's one fact we'll be using a lot, is that if you're working with sort of the weight lattice or character lattice at the level of algebraic groups, you only get integral things. So the integral adjective is just automatically part of the root data. But now, if we want to define co-roots, we run into an issue, which is that we no longer have a killing form to just give us the correspondence for free. So we need to do a little bit of work. And here, so if we start with a root alpha, what we do is we're going to use the analog of so-called SL2 embeddings in the Lie algebra setting that are associated to every root. So in the Lie algebra settings, each root alpha comes with an SL2 embedding by looking at the three-dimensional subspace of G given by taking the root space of alpha, all of which are one-dimensional, together with the root space of negative alpha, together with so I wrote H, but I have the feeling that that's not quite right.
You're right.
With respect to a given element X, right?
Oh wait,
maybe.
Yeah, it's a one-dimensional subspace of H. Yeah, like it'll
a
K times
one-dimensional
X for
subspace of H.
something in H.
Exactly. Yeah, and the idea here is we use the fact that root spaces are well behaved with respect to the Lie bracket on G. So we use the fact that if I Lie bracket G alpha with G beta, I land in the root space associated to their sum. In particular, if you check the generator of G alpha and G minus alpha, you end up somewhere in the Cartan. And you can just take the span of such a thing and get this three-dimensional subspace that's closed under the Lie bracket structure. And it turns out that there is actually an analog in the setting of algebraic groups, which will allow us to define co-roots. And this goes as follows. So we have a proposition that says, let's start with a root alpha of G, so an algebraic map from G to Gn. And choose some element x in the root space, non-zero. Then there exists a unique algebraic map, so an SL2 embedding from SL2 as an algebraic group to G. Let's call it phi sub alpha, such that first, if I look at the torus of SL2, so all those elements of the form T inverse for T in Gm is mapped. So let's call this T sub SL2 is mapped into T by phi alpha. The second property is that the differential, so phi alpha lower star from little SL2 to the Lie algebra of G takes the element E in SL2, little SL2, into the span of X, where X was this element of the root space we started with. And the last condition is that the restriction of phi alpha to the torus, which we can identify with Gm, satisfies that it's the image of the generator, so we'll call this alpha dual, and it satisfies that the pairing between alpha and alpha dual is true, where we use the pairing between the weight lattice x star t and x upper star t, and the co-weight lattice x lower star t, which is co-characters of t, mapping into z, which is really just composition. So if I have a weight alpha and a co-weight beta, I just send it to alpha composed with beta, which is a map from Gm to Gm, so I can view it as an element of Z under the identification we made earlier. So we've mimicked the construction from before in that we've found a co-root associated to alpha as the co-character associated to alpha under some SL2 embedding. And we've recovered this condition that we mentioned was satisfied earlier for co-roots in the Lie algebra setting, which was that whenever we pair a root with its associated co-root, we get true. And so this gives us now a set of co-roots. Which we denote by delta dual as a subset of the co-character lattice by sending each root to its dual. And now we have enough combinatorial data to actually write down a translation of the classification of algebraic groups, the reductive ones, into a combinatorial question. So we can now define a mapping where I work with connected reductive algebraic groups over C, and a map to so-called root datum. And these will just be a collection consisting of, for a choice of G and T, the character lattice with its associated root system, and the co-character lattice with the co-root system. Yeah, so that's the combinatorial translation of the problem of classifying reductive algebraic groups. Before sort of talking about this in more detail, one key fact which is important for the purposes of our mini course is that the collection where I reverse weights and co-weights and roots and co-roots. So if I just look at first co-weights and co-roots, then weights and roots, that's also gonna form a valid root datum. So that the fact that this actually gives me a correspondence. So this is actually, which is a correspondence. So the fact that this gives me a correspondence means that I can now define the Langlands dual group of G to be the reductive algebraic group associated to the reversed group title. So that was a lot of terminology in very little time. So I'll work through the example of SL3 to sort of illustrate everything. So let's fix G to be SL3. The torus to be as before. So these triples T1, T2, T3 with product 1. So I'll tell you what the roots are, what the weights are, what the co-weights are, what the pairing looks like, and what the Langlands dual is. So X star G, so those are gonna be maps from G to GM, algebraic maps. This is gonna correspond to maps of the form so I'm gonna act on an element T1, T2, T3, and it's going to send it to something from T1 to the A, T2 to the B, T3 to the C, where A, B, and C are some integers. And we have one more condition here. So because this product of T1, T2, T3 is required to be 1, this allows us to do the following. So this gives us a map by like checking exponents. From Z3 into the weight lattice. It's surjective. And the condition on elements of T gives us that the kernel of this map is given by the span of the element 1, 1, 1.
Hey, Saad, sorry to interrupt. Could you make Aaron a co-host?
Oh, of course, yeah. Let's see. I just gotta find him. Okay, there you go. I should make you one too, Alberto. If I didn't, oh, okay, that's done already. Cool. Okay. So if we look at, is it good? Okay, I'll assume it works. It looks like it did.
Sounds good.
Cool. Okay. So yeah, if we look at weights of associated to SL3, we have this surjection from Z3 with kernel one-dimensional kernel, and this identifies the weights of this torus with Z with 3 generators A, B, and C modulo the ideal generated by A plus B plus C. So this looks like a Z squared. And in general, SLN will have Z to the n minus 1 as a weight lattice. So those are the weights. Now for the co-weights. So these are homomorphisms GM to G. So these look like G goes to G to the A, G to the B, G to the C. A, B, and C integers. But now the condition applies in the image and tells us that A plus B plus C has to be 0 because G to the A plus B plus C equals 1. And what this gives us is that we can identify x lower star g with a hyperplane inside of Z3, where H looks like Z2 and is given by just the elements in which this holds. So once again, we can identify x lower star g with z squared. And now for the pairing. Pairing here is given by taking a pair starting with a weight. So I'll just copy it. Take a weight and a co-weight. And I compose them to get G goes, and if you do the composite, you get G to the A prime, G to the B prime, G to the C prime, which is identified with the integer A prime plus B prime plus C prime. So i.e. this looks like the standard inner product. On Z3. Cool. And finally, although I won't be proving it, if we reverse weights and co-weights and roots and co-roots, we can recognize the root datum of PGL3. Yeah, and so these are so that SL3 Langlands dual is given by PGL3 and vice versa. One comment I should make is in terms of the properties of this operation, that is Langlands duality. Taking Langlands duals factors through types in the Jenkins diagram classification. And we have, although I don't have it here, I think that most types are self-dual. So I think A, and Alberto, correct me if I'm wrong, G, E, F, G, self-dual types, meaning that if I take, for instance, an element of type A, I'm guaranteed to land in type A again. And B, C exchanged. Okay. So that's root datum and Langlands duality. Now we can state the classification theorem of representations of algebraic groups, which is very similar to the case of semi-simple D-algebras. So although I haven't formally defined it, dominant weights in this setting. Well, I guess before I go there, are there any questions on the root datum part of the conversation? Okay, cool. I guess the chat is quite active, so that's always an option as well. So dominant weights here are defined similarly to the Lie algebra setting. And I'm just gonna ask lambda a given co-weight to evaluate on each co-root. A given weight to evaluate on each co-root to a non-negative integer for every simple root alpha. So I have a weight, I check a co-weight, I apply the pairing, and I get a non-negative integer. And so with that adjective in place, we now have the classification theorem. that, so if we take G as before, connected reductive group over K with a choice of maximal torus G, irreducible representations. So we have a one-to-one correspondence. Representations of G. One-to-one correspondence with dominant co-weights, the dominant weights. In the weight lattice X star T. And we can, if you'd like to sort of put that next to the Lie algebra correspondence, you could differentiate each irreducible representation to obtain an associated E-rep of G of the Lie algebra G. Now G here is reductive, which for which an equivalent definition is that it splits as a direct sum of a semi-simple part and an abelian part. Likewise, if you're on the level of weights, a weight is just a character on the torus. If you differentiate that, you get an actual weight of the Lie algebra G. And because we only have integral things upstairs, we only map into integral things downstairs. So here you also map into integral dominant weights. Of G. Except now we have a little caveat, which I believe is right, but anybody should feel free to correct me, is that here we have a dominant weight, integral dominant weight of the semi-simple part. And then if we want a one-to-one correspondence between this direct sum of a semi-simple and an abelian part, and the right-hand side in the bottom, we need to actually add the contribution of the abelian part, which should be as many copies of G as there are dimensions in the abelian part, and only check non-negative objects. And now this should give us a correspondence. So this, I believe, is how the sort of classification theorem of either end should work out, and how they're related. And one more structural thing that this classification theorem gives us, this also sort of shows us how the full category of representations is built. Since it is semi-simple, it just identifies simple objects. As above. So that's good for us. It gives us a full understanding of what the rep theory side of the geometric Satake correspondence looks like. It has a bunch of simple objects indexed by dominant weights, and the rest is obtained by taking direct sums of such things.
Wait, you need to say simply connected, right?
So the simply connected part has to do with whether or not this map is a surjection, I believe. I'm not claiming it is, but there should definitely be an inclusion of the dominant weights on the algebraic group side into the dominant weights at the Lie algebra side.
Yeah, that makes sense. Thanks.
Yeah. Okay, so that's the classifications of those representations. And before we move on to sort of the talking about the Y group, there's one last kind of thing I want to talk about. It's a partial order that one can impose on weights and the notion of a regular weight. So just a little more weight theory. And I'm introducing those because they'll be useful when we move on to actually studying the affine Grassmannian and so on. So one is that we can impose a partial order on the weight lattice by declaring that, say, two weights alpha and beta are such that alpha is less than or equal to beta if beta can be reached by starting at alpha and adding something in the root lattice. So remember that this is equal to just the span of the roots. My bad. That's not quite what I want to say. That's too strong. I can only check positive roots, and I can only check non-negative integer linear combinations of them. So my bad. This is the ordering. If I sort of in the SL3 picture, this says that I can start here and then I can sort of move using positive roots kind of up. And everything upstairs is greater than me. Yeah. And then if you just reverse everything, you also get a corresponding partial order on the co-weight lattice. Right. And the second thing I want to briefly mention is regular weights. So a regular weight will be one such that if I evaluate it on every simple root, if I evaluate the co-root associated to it, I get something non-zero. So this is quite a geometric statement because the condition mu alpha being 0 has to do if I pass to the level of H star with belonging to the hyperplane H alpha orthogonal to alpha. And so to say that every simple root pairs in a way that gives me a non-zero integer tells me that I'm away from all of these hyperplanes. And we'll see in a moment, if we reach that today, that this means I belong to the interior of one of the Weyl chambers, of the positive Weyl chamber, actually, of my carton. Okay, I'm not sure about the positive part, but I definitely belong to the interior of a Weyl chamber. Yeah. So those are regular weights, and there's one sort of key example of a regular weight, which is called 2-row. It's kind of a weird name, but key example. Regular weight. So it's defined by just saying, well, I just take the sum over all positive roots. And I get a valid weight, and the claim is that this is regular. And the way one can go about showing this is by saying, well, let's start with a root. If I apply 2-row to it, I first get the root to its associated co-root. I first get the root applied to its co-root, where this is shorthand for beta paired with beta dual. And we've seen by construction that this is true. And then what's left to evaluate is the sum away from beta, so delta plus minus beta, of alpha applied to beta dual. And so if I can show that this is 0, then I get that I evaluate to true on every co-root, and so I'm good. And this is actually not too bad to see. This uses something that we'll define in a moment. So if we let H alpha be the hyperplane as above, with associated reflection in H star given by S sub alpha. So this is an endomorphism of H star sending an element. Let's see if this is the best way to write it. Okay, I want to actually define, let me see. I don't want to spend too long on this because we only have 10 minutes. So how about this? I'll skip this for now because I'll just get sort of confused by the notation, and I'll just say that the associated reflection S alpha preserves the set of positive roots, take away alpha for every alpha. And this symmetry leads to the identity where all the sum of all roots away from beta can be shown to equal itself minus a half sum of alpha beta. And so this must vanish. And for more, see page 7 of the notes on Slack. So this gives us a regular weight, 2 row.
Sorry, quick question.
Yeah.
When you say check for a beta in delta, should that be a delta plus?
Oh yes, my bad. Yeah, start with a positive root or a simple root, really.
Thanks.
Yeah. Yeah, I mean, it wouldn't make sense otherwise. I mean, otherwise the taking away the beta from delta plus wouldn't do anything. Good.
Also, just to emphasize, not only is it regular, but it is exactly 2 on every co-weight, on every co-root, sorry.
Exactly, yeah. You actually get this equality that's stronger. Yeah.
Only on the simple ones.
On the simple ones, yeah. Yeah, that's true. Maybe I should put simple here. And I mean, the reason I focused on this regular weight in particular so much is that later this will be involved in studying the Brouhat type decomposition. Of the affine Grassmannian. And that's something Alberto will check on day 3 or 4. But I guess to make sense of the Brouhat type decomposition, I thought I would start by talking about the Brouhat decomposition. And to do that, we first need to briefly introduce the Y group of G. So next section, we'll talk about the Y group and the Brouhat decomposition. And we'll probably have to stop more or less midway through this section and then pick up next time, which is okay because the Brouhat decomposition is also the first step towards talking about perverse sheaves in our settings. So let's try to at least define the Y group today. So I have twice the work because we present 2 approaches to defining the Y group. So either working in the Lie algebra setting or in the Lie group setting. So in the Lie algebra setting, it's quite straightforward. So the idea that to keep in mind is that W takes care or compensates for the ambiguity involved in choosing a Borel. And we'll see a couple explicit versions of this idea. But you should think as the Y group as just transitioning between different choices of B or the resulting positive roots and so on. And so I guess the most geodesic definition of the Y group is the Y group G is defined to be the group generated by all simple reflections in H star, i.e. W is defined to be group generated by the set S. S is the set of all S alpha, such that alpha is a simple root. Where S alpha geometrically, as we said, is given by reflection along the hyperplane orthogonal to the root alpha, but explicitly S alpha of X can be defined as taking X minus 2 times alpha X alpha alpha. So that's basically taking the weight associated to the killing form and multiplying by the killing form applied to X. So that's just sort of a hands-on definition of what the Y group is, although it doesn't really give us sort of a global understanding of what it does, maybe, or its structure. Let's see. But we can already say a few things at this level. Is first of all, the action of W on H star restricts to a group of permutations of the set of roots. So it respects the roots. And in fact, this can be shown to actually be a finite group from the fact that the roots actually generate the carton. And to say a little more about this sort of taking care of the ambiguity, we can talk about the fact that if I start with an arbitrary, start with a weight lambda in H star, then its Weyl orbit W acting on lambda contains a unique dominant weight. That one can find given as the maximal element with respect to the weight ordering defined above. And I guess what I really mean here is, again, the same kind of ambiguity or transformation where you start upstairs in characters on T and you differentiate in H star and you act on that. And you get a set of elements and you declare one of them to be dominant with respect to the Weyl order, to the weight ordering. And one last remark here, that's also in a similar way, sort of looking at orbits under the Y group. So you can decompose H star minus the union over all, I believe, it's either positive or simple roots. But maybe Alberto can remind me which one it was. So I guess all positive root, all roots, I guess. Yeah, I mean, it doesn't really matter. If I take away all of the hyperplanes orthogonal to all of the roots in my set of roots, I get a subspace that I can, or a subset that I can sort of, for which I can take connected components. So I get open connected components called Weyl chambers. And it turns out that W acts simply and transitively on those. And that something which I had mentioned before, regular weights constitute one of the weight chambers, which we call the fundamental weight chamber. Cool. And as a little sort of quick example, if I take SLN, then my while group will actually just be the full symmetry group on n ladders, and it will act on the torus, which is just diagonal matrices, by permuting them around. Yeah, so I'm not sure whether or not I should stop here, given that we've sort of started 5 minutes later. But yeah, I guess maybe it's good to stop here and resume tomorrow, just so as not to run for too long. Any questions?
I have a question.
Yeah.
I think I got confused with notation. So
Yeah, fair.
when you write the normal parentheses, is that the killing form?
Yes, so this map S alpha is defined on H star, and when I'm in H star, the parentheses always mean the killing form.
Okay.
So there is sort of, I think it's kind of like a harmless ambiguity in that you have a pairing upstairs between weight and co-weights, and you have the killing form downstairs. And I think that if you differentiate weights and co-weights, you actually should preserve the killing. You should have a correspondence or an equality in terms of the pairing upstairs and the killing form downstairs. It's something I'm still kind of trying to figure out, but that's my impression so far.
Wait, okay, so if you apply the parentheses to two elements in the H star, wait, so sometimes it means the killing form and sometimes it doesn't?
So,
right.
So upstairs you have this pairing between weights and co-weights going to Z. If you differentiate a weight, you end up in the integral the integral weight lattice of G. So that's gamma G.
Okay.
And I guess now the question is, so these two both live in H star. So let's see, if we only take the root lattice here, then under the co-root correspondence, I can actually identify this with that, and here the pairing, the killing form gives me a pairing. This is just a composition pairing, and I think at least at this level, the pairings should coincide.
Isn't there something like slightly off? Because there's two maps from like roots to H star. There's the killing form, just like a bilinear form gives isomorphism to the dual, and then there's like the scaled version.
Oh, so the root goes to a co-root, and the root goes to its associated functional, yeah.
Yeah, so the map from a root to a co-root is not just the killing form, right?
Yeah, the map from a root to a co-root isn't just, it's the killing form after scaling, yeah.
Okay.
Yeah, yeah, I'm still not very clear on this, so that's really a big question mark, and I'm not sure yet how those two correspond. But it's true that there are pairings downstairs and upstairs, and there's still a question of like which one does what.
Okay. Well, the reflection formula makes sense if that's the killing form, I think. Yeah.
Yeah, that's the reflection formula is definitely involving the killing form. That's for sure. Yeah.
Cool. Thank you.
Yeah.
Can you scroll down to the bottom?
Oh, yeah.
Just so I can see.
Okay, I'll hang out for a couple more minutes here, just in case anybody has anything, but thanks for coming, and yeah, hope to see you again tomorrow. Cheers.
Thank you.
Yeah, thanks.
Awesome.
So many questions on the chat.
I have a question
Yeah.
about the Tanakian reconstruction.
Mm-hmm.
So if I remember right, the H that you get is the sort of natural automorphisms of the fiber functor. Is that right?
That's a question that Alberto should be.
Yeah, that is true. Yeah, so you can sort of construct H like out of this by taking the automorphism in the fiber functor. That's not really a perspective which is going to be relevant for us because we're basically going to find H, and then instead of like constructing it like that, we're just going to sort of look at its root data to like identify it. But in general, that is true. Like you can construct H. H is precisely defined to be the automorphism of the fiber functor. Yeah.
Okay, in that case, how does H get the structure of an algebraic group? Is there some structure with the fiber functor that I'm...
That's a good question, which I'm not sort of automatically seeing the answer to. I mean, it's definitely going to be sort of K-linear, and it's definitely going to be a group. So whether it's, I guess, has the structure of a Lie group or algebraic group, it's not sort of immediately evident to me, but yeah, it's not immediately evident to me. But
There's real work that's done. Like the Tanakian formalism is a theorem for this reason. Like there's many things that are being said there. It's like it's an algebraic group, it's an affine algebraic group, and like, well, I guess those are the two. But yeah, like it's not immediate that like this is obviously an affine algebraic group or something. Like you still have to do work.
So it's not like there's some obvious embedding into GLK that I'm missing. There's like some real math that you need to do.
yeah, I mean, I would just be guessing if I said something. I mean, my first guess would be to try to like look at the simple objects of, well, yeah, I would just be guessing. Yeah, I don't see an obvious map to GLK off the top of my head.
Okay, cool. Where does someone have like a reference to something I can read on this?
Yeah, so Tanakian formalism is kind of one of those subjects that's not amazingly referenced in too many places. Most places just kind of like use it for the theorem that they have to and don't really, well, they do exactly what we're going to do, which is not really go into the details of it. But having said that, there's a paper by Bowman and Risch where they basically follow Mirkovich and Vilonen's paper and prove geometric Satake, where they actually do have a section, like the second section in particular, the first one after the introduction, where they actually do prove the Tanaka stuff. Yeah, I'm seeing, I think Tom put a link. I'll drop my link too. I wouldn't be surprised if Tom's is better, but because this is still like a paper that's proving geometric Satake and just has a section on it. But the second section of the paper I sent actually goes through and does all the work, which the original paper doesn't bother to do.
Okay, cool. Thank you.
What about Pramod's book? Does it have anything on it?
Pramod's book, I mean, it references it because you need it for the proof, but as far as I could tell, it does not prove it. I think he just has a short section where he states the theorem, and then, yeah, I'm kind of looking through that section right now, and he has some words. It's on page 620 if you want to peek at it, but there's not a proof in any capacity. It's just like basic exposition.